Hello everyone, good evening. Welcome to week 12 live interactive session of NPTEL ACN course. My name is Ranjita and I'm a PhD scholar from Department of CIC IIT Hyderabad. So we'll be quickly going through the topic discussed in the previous week, that is week 12, which is named data networks, and we will look into the questions. It's a small topic, so we'll look into those questions and then we'll try to recap on various topics that we studied in this full course. Let's get started. So NDN is the topic discussed in the previous week. Mm, So it's a new kind of a network that people are trying to design for the majorly for the content that is majorly over the internet these days. What are the major contents? Like 50, 60 or maybe more than that percent of the data in the network is currently from the multimedia content from applications like YouTube, Netflix, all the streaming sites, Amazon, etc., etc. Okay, so there was a attempt done to come up with a new network design that would cater to these kind of applications. So when such a network design was considered, there was two design choices to define such a network. One was to have the underlying IP network in place, overlay a mechanism wherein have the underlying IP in place, and then design the network on top of it. Another one was like clean slate approach. So the NDN, so in clean slate approach, we don't even assume that we have the underlying IP network in place. So it is what NDN have tried to come up with. So the concept of IP-based addressing, nothing is there. I didn't. So in this clean slate approach, they start from scratch actually. There is no concept of IP address or anything. Whatever was the previous or the traditional network mechanism, it's completely forgotten. Existing is not considered. A new network is designed. that cater to the content-based application. Is designed, and in NDN they have gone for this clean slate based approach instead of overlay. Okay, so the major design principle here is like in the traditional TCP/IP, we have the sender-based, sender-driven. So like we request data and we give it. This is like receiver-driven. Packets are sent to the destination. So major difference between the traditional IP and NDN is that this is NDN is receiver-driven. Majorly receiver driven, and the data content. So the data content could be a file or video or an audio or anything. So data chunks are retrieved, and the NDN routers are routers are stateful. So we'll see what all this means. What is the stateful meaning of NDN? Okay. So if you're sending this file, it can be divided into chunk 1, chunk 2, chunk 3, and chunk 4. And these chunks could be individually sent one by one. That's what that is the idea of having the idea of NDI. Okay, uh, rather than the concepts of packet, we have these chunks actually. So basically, in NDN, we have majorly two kinds of packets. One is the data or the one is the data packet, that is the content or the chunks, and the other is the interest packet. So basically how it works is if a particular person wants to get details, so and these are the routers, and this is the and here we have the concept of producer, and this guy is the consumer. Okay, so the producer is producing the data, and consumer will consume the data. So producer will send a request for the data, or it will show an interest in the data. Interest is shown to this data, and then the data is shared back. That is the basic concept of NDN. So we have this two types of data packets. One is the data, two different types of packet. One is the data packet, and the other is the interest packet. So the format or the not exactly the format. So typically in the interest packet, we have to tell what is the data, the name of the data. That is something that will be there in the interest. Name of the packet will be there. Then maybe you can also tell that, okay, I need it from this particular producer kind of thing, like I want it from this publisher, and if the publisher is delivering it in certain way, then I need it. So some kind of selectors and filters can be applied. Filters can be applied, and so that is another thing that we will have. Another thing is nonce, which is typically used to identify the interest packet and the data packet, and then we have something called guide. So these are the major things that will be there in an interest packet, and in a data packet again, name, then some metadata information. Metadata information will be there. Then we will have the content. So it could be the file, it could be the YouTube video, it could be the audio. So content could be file, video, audio, etc. and then signature. So this is the interest packet and this is data packet. The basic content. So metadata, in metadata, you can tell that, okay, this particular content is valid for so many hours, or various other content type, the uh, validity period, etc., can be mentioned in the metadata field. Signature field is basically used to ensure the integrity and authenticity of the packet. So when this data packet is in transit, it should not happen that somebody modify it, or by due to some transmission related issue, there shouldn't be any corruption happening, right? From here to here, when the data packet is in transit, to ensure that the content the producer is giving from here, okay, it is R1, it is R2, and it is the consumer. Okay, so to ensure that he have given such a packet, and to ensure that what is received by the consumer is exactly the same. So this is X, and then what should be received is also X. So we have some mechanisms for integrity and authenticity. So here what is used is signature. Signature and helps ensure that, okay, nobody have modified the data in transit. So the producer will sign, basically it is equivalent of signing the document like this, and the signature will attach, and how the signature is generated, that the consumer will be aware of, and the consumer will also generate a similar signature using the similar technique, and check if it is, if this generated signature and the one that is that so this particular signature is appended in the document. So this is the generated one, and there is a signature in the in the packet, so that will be matched across. So if it is matching, it implies that nobody have modified it in the middle, so there was no corruption or any issue. Otherwise, it implies that, okay, the one that is received is not what the sender have actually sent. So that is about the interest packet and the data packet. Now, so this one name. So this is how does one name the content? So certain naming conventions are followed majorly in NTN. The naming convention followed is hierarchical naming. Hierarchical naming is what is followed. And it is normally that naming is done by the developer who creates the content. So in hierarchical naming is something like the b/1 dot mpeg, like that. In a like how we have our URL in a similar manner, this is how the naming convention is used. In certain very special cases, only flat names are used. Hierarchical naming is mostly used so that it will help aggregation. Like in Indian also, there are routers that follows the packets, right? So when a request comes, request will go and then the response comes. So when a request comes for a particular content, the router should know, okay, whom should I go? Whether I should go to R1 or R2 or R3. If there is a R1, R2 or R3. So this could be a one producer. This is another producer. This could be a third producer. So, based on the content name, the router should be able to route the interest to the corresponding next router and the producer. So, when we have the hierarchical naming convention, it is easier for what to say aggregation, and this can work in the form of a longest prefix. So that's the reason Indian have gone for a hierarchical naming convention. So one thing here to be noted is typically the Indian like normal content when we are consuming, they are not like dynamically generated data, like I'm watching a movie on Netflix or Amazon or YouTube. But when we are having a live streaming, then typically the name is actually getting generated in a dynamic manner. So with live streaming, there is a dynamic data generation. So when I'm listening to a live stream, I should know the content, and I need to get the all the following chunks of data, right? As and when it is streamed in timeline, I should be able to receive that. So in such a scenario, both how it is taken care is both the producer and the consumer will arrive at a deterministic algorithm based on which the name will be generated, and then once the initial name is generated, further on the chunk by chunk the data starts coming to the consumer. So a deterministic algorithm is used. Okay. So now so we saw the naming. So in these routers that we have seen, typically the NDN comprise of three different kinds of tables. Okay. Routers comprise of three different data structure or tables. First one is the forwarding information base. The second one is the pending interest table. Which is PIT. And third is the content store, which is nothing but cache. Okay, so how typically like when consumer is requesting for a data, how it works is okay. So initially, what goes out is a so this guy all of them will have a forwarding information base. Okay, so in the forwarding information base, when a particular how the content will be is that there will be a name followed by like how we have in our normal IP routing, right? IP address and port number, right? Same way, which means that to which port we need to forward the packet to. Same way, we have something called name and router number, okay, or port number also. Next stop. So for an XYZ content, you send it to R3. Assume that we have, there is an interest packet coming at R1. So this interest packet will be looked up. The name of the interest packet will be retrieved and it will be looked up in the forwarding information base. So, okay, for XYZ, I have to share for send it to R3. So it will be sent to R3. Okay. So the interest packet will be forwarded to R3. In addition to that, what R1 will do is R1 will have a pending interest table. Okay. So to that table, it will add this particular request. So this interest request of XY Z to which I am forwarding, that will be added to the pending interest table. Okay. Then at R3 also, it will, if the FIB is, this is the producer. We will have X, Y, Z. It is probably gate number 1 or producer 1 or whatever representation. Okay, basically it tells that for X, Y, Z, you send the interest packet here. So the interest packets get sent, it reaches the producer and the producer will respond with the data. Same way R3 also will add XYZ to port 1 karke in its PIT, it will also add and keep. Okay. So now when a response comes, okay, producer, we can tell it as producer only. Okay, now when data packet comes, it will match it. So in addition to that, it's not only that PIT will have this info, PIT will also have the information of from where it came. Okay, it will have the information of R1 and this will have a information of consumer. From the consumer, this packet came which was sent to R3. So now when a response or a data packet comes, it will check the PIT. Okay, in the PIT, we will get the information. Okay, this request came from R1 and I had sent it to producer. Now I have got the data. So now this needs to be sent back to R1. So the data gets forwarded here. So for this purpose, the pending interest table is looked up to know that from where did, for which request did I initiate this? So for which interest did I send the request upstream? Okay. So when the data comes in the R3, it will clear off because now the response came, right? So it will clear off this entry and it will add it to the cache store. There is CS also, right? R3 will add it to the cache store. It will add the data like X, Y, Z. That data will be now in the cache store. Same way, now in R1, when it gets the data, it will check the PIT from where did the interest request come. It will see that, okay, it came from the consumer. So it also doesn't have anything in the cache store. R1 also will cache the data XYZ and it will clear the entry because now the response came, have the data, it will clear the entry from the PIT and send back the data to the consumer. So at a later point tomorrow, if a different consumer comes, so if another consumer came, like this is C1 and this is C2. Now if he sends an interest request, R1 for XYZ, interest request for XYZ, R1 will see the forwarding information base. It will see the cache store also. Okay, every time when a request comes, it checks the cache store. Okay, so it checks the cache store, it have the data. So then this data will be taken from the cache and responded back. It will not go to R3 and the producer to collect the data all the way. Same thing if another consumer some C3 comes to R3 for the same data XYZ, then R3 will check its cache store XYZ is present, so that data will be sent back to C3. It will also won't send the interest to the producer because it already have the data. So if we see it as a flow, so at the router, first cache will be looked up, cache store will be checked to see if the data is present. Data or if the content is present. Okay. If yes, first the cache store will be checked. If yes, respond back. Else, add to pending interest table, forward the interest, look up the FID. forwarding information base and forward the interest. Okay. So this is typically what happens on getting a request. Okay, on receiving an interest packet. Now on receiving a data packet, again, normally it will not be in the cache, because if it was there in the cache, definitely it wouldn't have send the request to the upstream. So update the cache. Then look up PIT to where the interest came from. Then send the data, clean up the PIT, clean up PIT entry, not clean up, delete. Delete the PIT entry. Then after that, forward the data to the requester. The one who requested, the consumer. Okay. Okay, so this is broadly how it typically works. Okay, and another aspect in name data network is that in a name data network, as we saw that uh, we get the request, right? So we get the request. We get a, so suppose that we have another path also. So I got a request here and I've sent it here this way. So the response will not go, I mean, it will never go like this. It will never go this way. Okay. The response will always go in the same path where how the request was processed. So in that way, the request reply in NDN is like symmetric. Because what happens is in the PIT, when a data is sent, we add an entry in the PIT. Here also PIT entry is added. Here also PIT entry is added. Okay. So the PIT entry will tell from where the request came from. So when I get the data for this request, for this interest, PIT tells from where this request came from. So it will tell that the request came from R3. So as the request came from R3, the data will also, as the request came from R2, the data will also go to R2. So R2 also would have tracked that the request came from R1. So the response or the data for that request will always go to R1. So this is ensured in the NDN. So it's symmetric. We can take an example which the one that sir have in the lecture. So we have a router here. We have another router here and another router. So we'll just take a simple example. We have a So the content that the client is requesting is like uh, some XYZ dot B and this R1 and R2. Okay. So the FIB in R1 is, so it will have FIB, it will have PIT and it will have CS, right? So FIB, so if we take it as a big box, in the FIB, uh, suppose we had this abc.ef. Okay. If such a content comes, we forward it to R. Okay. This is what the entry was in R1's forwarding information base. Okay. And it doesn't have, its PT is as of now empty. PIT is empty and its cache store is also empty. Nothing is there. PIT is empty, cache store is also empty. Same way for R2, we have FIB, and in FIB it is written that if I get a content ABCEF slash, you give it to share it to publisher. The PIT is empty and the CS is empty. Okay. So now what will happen when a request comes? So let's see the changes in the tables one by one. So when the request is going, it reaches R1. R1 does the first lookup in the cache store. Cache store is empty. Nothing is there. So it understand that, okay, this content is not there in my cache. I need to get the content. So it will look up, okay, this is the request for content ABC/EF. Okay. So ABC slash EF can be got from R2. So the request will be sent to R2 and an entry will be added in PIT table. PIT table slash ABC slash EF. The request came from subscriber. So this is the subscriber. So the request came from the subscriber. This entry will be added into the PIT table. Okay. Now on R2 will receive the request interest. R2 will also see if the cache store is empty or not. Whether ABC, this content, the content with the name slash ABC slash EF, if it is there in the cache store or not. Here it is on empty. So the content is not there. So it will R2 will look up into its forwarding information base and it have that entry telling that, okay, if the content name is ABC/EF, you send it to the publisher. So it goes it to the publisher. Okay. And at the same time, R2 will also add an entry to the pending interest request. So this request is pending at R2. R2 needs to respond back to R1 when the response comes from the publisher. So that information it will add in the PIT. So from where did the request come from? Request came from R1. So this information is tracked so that when the response or the data comes from the publisher, it can send it to R1. Now, when the response comes, so now when the response comes back from the publisher, when the data comes, this is interest. Okay. Now, when the data comes from the publisher to R2, first, what R2 will do is R2 will see, okay, this data has to be added to its cache, right? The cache was not there, so it will add the data to the cache. Name, it will be ABCEF and the data will be added to the cache store. After that, it will see the pending interest request to know that who gave me this request. Okay, from whom did I receive this particular interest request? So it will do a lookup into PIT. When you do a lookup in PIT, it will get to know that, okay, I got this request from R1. So R2 now knows that, okay, the data I need to send it back to R2. So it will send back the data to R2. Also, it will delete the entry. The pending interest request is a pending request. As soon as the request comes, this will be deleted. Now there are no pending requests at R2. Now at R1, when this data comes, R1 first will add it to its cache store. Doesn't have in the cache store, so it will add the content to its cache store. The data will be added to its cache store. Then it will check PIT. PIT, it will check, okay, from whom did I get this request from? So it received the request from the subscriber. So it will send the response or the data back to the subscriber. It will also delete this particular entry from the PIT. So now, if suppose R1 gets connected to a different subscriber, okay, different subscriber S2. So now when S2 makes an make a interest request, R1 will first check the cache store. Okay, cache store, it has the entry, so it directly respond back with the content. Doesn't give it to R2 and all the way to the publisher. Same way, if R2 have another subscriber connected like S3, then and if it gets a request for the same data like slash abc slash ef, then R2 will also check its cache store. Cache store mean data is there in the cache store. So it will respond back with the data. It will not go to the publisher to get the data. So this is how basic, simple way how the FIB and PIT is used, and how basically the content or name data network works. Okay, so with such a network, with such name data, as we can see, we are having stateful routing, right? So it's actually remembering, it's caching. The routers have forwarding information base like our normal router, but in the traditional routing table, it doesn't store the data, right? It doesn't store the content. It doesn't keep track of from whom I got the request. So request and response is not always symmetric or symmetric. Like the path that the request taken, it may not be always true that the response also would take the same path. Okay, whereas in NDN, request and response will take the same path. So interest and data will take the same path. That is interest, and the corresponding data for that came for that interest will take the same path. Same way, since this caching happens, suppose we have a router here and we have a like how I showed, two of them are connected. Okay. Now, both of them ask for both of them, okay, let's take the same scenario. Both of them ask for ABCEF, okay, in the, okay, XYZ, 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 okay, and this is a router, and this is where the publisher is, okay. So here in this routing table, how it will be is R1, R2. So for R1 FIB, we know XYZ, you give R1. I mean, sorry, R2. Currently PIT is empty and CS is empty at R1, and R2 also FIB is XYZ publisher. This is P1. Okay, let's go to P1. Then PIT is initially empty and content cache store is also initially empty. Now when a request from this is S1, this is S2. Okay. Now when a request from S1 comes, R1 will see, okay, cache is empty. So I need to send it. It will check, okay, XYZ. I need to send it to R2. So it adds an entry XYZ. The request came from S1. It will send this request here. Okay. Now the same thing will happen. R2 will at the same time now if S2 also sends a request. S1 say one request and S2 say another request. So now S2 from S2 if it gets a request it again checks okay the CS is empty but it will see that already there is an entry in the XYZ S1 which means that already it have sent out the request for XYZ to R2. So it what it will do is it will drop this request, drop the interest, but it will add an entry to the pending interest request. Because the request is still pending at R1. R1 need to serve both S1 and S2. But since both of them are asking for the same content, only one interest will be forwarded to R. So one interest will be dropped and the other will be forwarded to R. But R2 will repeat the same thing. It doesn't have the content cached. So it will mm, check the FIB and it will add the entry to PIT. XYZ, send it back to R1. And then the publisher will come back with the data. So it will add it to XYZ and this PIT entry will be deleted and the information will be sent to R1. Okay. Now at R1, it will add to the cache store. XYZ will be added to the cache store. Data. And then it will check the PIT. Okay, in the PIT, XYZ needs to be sent to S1. So data will be sent to S1 and XYZ need to be sent to S2. So both of them, R1 will send the data and then it will clean up its PIT. So that is how so this is possible because of this PIT. In the normal traditional routers, if S1 is requesting, S1's request will go all the way via R1, R2 and P1. S2's request also will go via R1, R2 and P1. But with NDN, it doesn't happen like that. If two people connected to the same router request for the same data, only one request gets forwarded to the destination. The other will be dropped and but the router will keep track of who all have requested those data. Now in this scenario, instead of XYZ, if S2 have requested some other new data, then both the request will go out. Okay, so that is how NDN works typically. Now, if the situation is like another similar kind of situation, the screen is visible, right? Okay. Now, if you see another scenario, for example, we have another one subscriber here, S1, and another subscriber here, S2, and it is connected to one router. This is connected to another router, and then both of them together is connected to another router. And then this router is connected to another router, which is connected to the publisher. Okay. Now suppose both of them are asking for XYZ data. So what will happen is in R1, R2, R3, R4. Okay. In R1 and R2, this will be added to the PIT. So R1 PIT will have XYZ, XYZ, S1. R2 PIT will have XYZ because initially the content store is empty for all of them, right? For R3 will get the same request from R1 and R2, right? So its content store is empty, so it has to send it here, but to its PIT, it will add only, to its PIT, it will add both of them, R1 and XYZ R2, but only one request will be sent to the upstream router. Now, when the response comes back, R3 will check, okay, I need to send it to R1 and R2. So it gets sent to both R1 and R2. It will then finally delete this. Then at R1 and R2 also, it will get forwarded back to S1 and S2. And all these people will start caching those contents. So at a later point, if a third S3 comes up and asks for the data, it will immediately get it because it's already cached in the cache stage. Okay, hope it is clear. Mhm. So then another aspect is basically the security mechanism here. Majorly security mechanism that is used in NDN is the signature, that is to ensure the authentication and integrity of the data. So data packets, authenticity and integrity is ensured using digital signatures. So authenticity means that I am receiving it from the intended sender. Like I am this producer P1 is sending, and when S1 is receiving, when you say this is authenticated, it means that okay, S1 is receiving it from P1 itself. No third party in the middle is coming in the between and sending any random things to S1. So that is what authentication means. You can be sure that whatever you have received is from the intended sender. Okay, from the actual publisher. And another thing is whatever the publisher have sent in the transit, like it's going from publisher to R4, R4 to R3, R3 to R1, and then to S1, right? So on the way, nobody modifies the content. Like if you're seeing some video, if it is a video content, if some of the frames was missing or it gets corrupted, on all those scenarios at S1, S1 should be able to identify that okay, whatever P1 have sent, I have received them intact without any modification or any change. That is what we call by integrity. Okay, so there are techniques in the computer science security side. There are techniques used, standard techniques used to ensure integrity. Some things are key based message authentication code, and another the most commonly used in the regular web browsers are digital signatures. Okay, so uh, these are the mechanisms. Signature is the mechanism used in NDN for ensuring security. Okay, right. Maybe we can now move on to the questions. Um, Okay, so the question one, so how many packets are used in used in NDN to retrieve named chunk from content provider. One, two, three, D, four. Maybe I'll copy paste the question in the chat. Easier. So anybody, you can type in the answer, then we can discuss. So how many packets are used in the NDN architecture to retrieve a named chunk from a content pointer, so content provider? So we just saw, right? So how the subscribers are requesting the data, right? So so there is a subscriber via multiple routers. There is a publisher, which is the content provider. So we have seen that first it sends the interest, then the goes interest goes all the way to the publisher, then the publisher responds back with data, right? So how many packets are needed? Two different types of packets used in NDN. You can type in the answer. So we need two types of packets, right? One is the interest packet, which is sent from the subscriber, and the second is the data packet, which is sent by the publisher. So there are two packets are used, okay, to get the name chunk from a content provider. Now the second question, I'll just copy and paste it in the chat. Okay. Right. So the question is what is NDN data caching? How does NDN handle data caching? So I think again I will just draw the figure. There is this router, another router, and the publisher. Okay. So we have seen, right? We have the FIB, then we have PIT. On all router will have these three things: content store, which is the cache, and this router also have it. This router also have the content store, PIT and FIB. So we have seen when the interest comes here, entry get added here, and then it goes. So XYZ comes. This is S1, this is P1. So an entry like XYZ, S1 gets added in the pending interest request, interest table, right? And then this interest goes to, it gets forwarded. So FIB have XYZ This is R1, this is R2. R2 and XYZ P1. Okay. So at R2 also, okay, the cache is empty. It forwards it to P1. So when the data comes back, the interest XYZ goes here. Now when the data comes back, what it does is R2 adds it to its cache. R2 adds the data to its cache. It cleans up the XYZ request came from R1. So it will send it back to R1. Same way at R1, what it does is it will add it. XYZ, okay, I have got this data, I will cache it. Now the request came from S1. So it will clean up this because it already, the request is handled and it is sending it back to S1. So as you can see, which answer will be correct by caching data on the end user device? Are we caching it on the end user device in NDN? Yes or no? So, can you see when a data request went, when an interest went and a data request came back, where all did we cache the data? So we did not cache it on end devices. Did we cache it on end devices? No. Did we do it on the intermediate routers? Intermediate nodes? Yes, R1 and R2 are the intermediate nodes. So we have done the caching on the intermediate nodes. Now, are we caching it on a centralized server? Do we have a centralized server here? We're not caching it on any centralized server. No, we are not caching it on any. Then the next one is NDN does not support caching. Of course, there is caching in place, so this is also wrong. So the correct answer for this question is B. How does NDN handle data caching? So data caching is handled by NDN by caching the data on intermediate nodes, that is on R1 and R2. Okay, is this clear? Next question, Q3. Which of the following statement? Yeah, just read through the question. We'll discuss. All of you are able to see the question in the chat, right? When I am audible, my screen is visible. Okay, thanks. Yeah, so the question is, which of the following statements is but are correct about named data networking and IP architecture? So NDN network, like IP packet delivery, employs best effort data retrieval. Second option is NDN has a stateless data plane, whereas IP has a stateful data plane. third one is IP includes a security primitive directly at the IP layer. One interest packet can fetch multiple data packets in NDN. The routing plane of IP is dumb, whereas the routing plane of NDN is null. Yeah. So, option one is NDN network like IP packet delivery employs best effort data retrieval. So, that is true. So, NDN also does best effort delivery only. Delivery of data packet. So, option one is true. Second one, NDN is stateless and IP is stateful. Um, which is actually not correct. NDN is stateful. It tracks from where the packet came using the PIT. It also does the caching. So in NDN, this is wrong. NDN is stateful. NDN is stateful, whereas IP is stateless. IP actually on the arrival of a data packet, we do not store any information in the data plane, right? We just look at the header and forward the packet. That's all. Whereas here, when an interest packet is coming, we are actually storing certain aspects of the packet so that when a response comes, we can reply back properly. So NDN is stateful, whereas IP is stateless. In IP, equivalent to IP, we have FIB here in NDN. But with if it was only FIB, then NDN also would have been stateless. But in addition to that, NDN also have PIT and CS. That makes it stateful. Okay. And the next option is IP includes a security primitive directly at the network level. That's not true. I mean, it depends where what kind of a protocol you are using. If it is like an IPsec kind of a thing, then okay, yes. But by default, it doesn't have any security primitives in place in the IP. It's an added protocols on top of it. So C is wrong. Option C, like security primitive at network layer. Then the last fourth option is one interest packet can fetch multiple data packets in NDN. Is that true? Can one interest packet fetch multiple data packets? So they are all named, right? So for an interest packet, you get only one data packet, okay? But this one exchange, using this one exchange, further on multiple interest packets on the same data can be like addressed. So for example, we have already seen here, no? So initially this interest packet went and you got the response. So the caching happened, and further on, if any number of new subscriber goes and asks for the same data,
the data will be given, but it doesn't mean that with one interest packet you get multiple data. So if you have requested for XYZ, you will get only XYZ. You will not get ABC or DEF. It is name, it's based on the content name only, the data packet will be obtained. So one interest packet, multiple data. So this is wrong. Okay. And the last option is routing plane in IP is dumped. But NDN is not. This is also wrong. It is not the routing plane that is smart. It's the tracking, the statefulness that allows certain aspects in NDN. It's not the FIB still works the same way as it works in the IP routing. Okay, but the addition of PIT and the CS is what makes it stateful and help us reduce the number of packets for the same content being exchanged multiple times. That doesn't make the routing plane in NDN smart. Okay, so the answer here is A. So this is A, B, C, D. Okay. Now the fourth question. So just read through the question. So we'll discuss. So the question is, which of the following problems is bar are addressed by the Indian name-based routing? So since there is no limit on the size of this name, it's a hierarchical naming that we use, right? So there is no issue of address space exhaustion. With IP addresses with the IPv4 32 with the 32 bit IP address, we could have 2 power 32 different IP addresses only, and so we had this issue of exhaustion, and then the IPv6 address came in. But with named addressing, there is no such issue that we have in NDN. It's a hierarchical naming, so there is no issue of address space exhaustion. Same way, why did this whole concept of NAT came in? The concept of NAT came in because of the IP address exhaustion issues. Because it was not possible to give each device present everywhere a unique IP address. So enterprises started within a particular enterprises. So different enterprises, they will get one or two public IP, and further on all the devices that are within the network, all will be in the private IP domain. So this will be all in the private IP domain. Then this private to public conversion is taken care by NAT. NAT takes care of private to public and back to private, public to private. So from the enterprise, if someone is accessing the internet, this conversion happens and it goes out with the public IP, and when the response comes back accordingly, it gets translated back and it goes to the correct person who made that request. So this whole NAT thing came up because of this lack of addresses. So as there is no address space exhaustion, we don't need NAT also here. So we won't need a NAT. So guarantee of no data loss, no. That doesn't, NDN doesn't give that. NDN is still based on the best effort service. So it is still based on best effort service only. So it doesn't guarantee any no data loss scenario. And then the address management. This whole concepts of address management also doesn't come into picture. It will be hierarchical name addressing. Okay. So this is also true. So the answer is A, B and D. So with name data network, we get rid of solve these issue like address space exhaustion, NAT traversal and address management. So the next question, 25. Let's read through it once. Which of the following is a key difference between content store PIT, like pending interest request table in NDN? Okay. Following is the difference between content store and PIT. Cache store, content store and PIT. So option 1 is CS is used to, so this is for forwarding interest to next hop, while PIT is for storing data. Second is, or no, let us see what it is. CS is used to store interest. Um, while PIT is to cache. See, go next. Okay. So let's see how it works once again so that we can easily answer this question. So we have FIB, PIT and CS. Okay. So when an interest comes, so when an interest interest for XYZ, XYZ to R2, and here it is. Okay. So when a request comes, as we have already seen, R1 will first see the cache store is empty. It will use the forwarding information base info XYZ to R2. So it forwards it here. It adds an entry for the PIT. So it will add XYZ to S1. So PIT, so the pending interest request is added to the PIT. Okay. Same way at R2 also it will see that okay XYZ, I don't have the content currently for XYZ. It needs to be forwarded to P1. And so it adds it to the pending interest table XYZ. The request came from R1. Okay. So with this in place, let's see PIT is for storing data. Do we store the response data in PIT? No. So this is wrong. PIT store data, again wrong. PIT store interest of pending request. That is what PIT is doing, right? It stores the interest of pending request. So whatever pending interests are there, that is being stored in the PIT. So this is correct. And PIT is used to forward the interest to next stop. No, that is FIB is used. So this part is also wrong. So let's one see how when the response come, what will happen is R2 will store the data. Data is stored in CS, and the pending request will be then removed and the data will be sent back to R1. R1 will again store the data for in the cache store, and the pending request will be cleaned up from. So PIT will hold only the unresponsive request, okay? Then it will be sent back to S1. So CS is for forwarding interest to next stop. No, this is wrong. CS stores the interest. No, CS stores the data, and CS is not for incoming interface. So this is the correct answer. Cache store is to store the data, and PIT is to store the interest of pending store the interest of unresponsive request. So C is the answer here. Okay. So the next question, Q6. Hmm. Yeah, just let's read the question once. Hmm. Which of the following is per are the reason why NDN may be more efficient than IP in terms of network resource usage? So, why is NDN more efficient than IP? Why is NDN more efficient than IP in terms of resource usage? Yeah. So the option is first one. Okay, maybe you can read through it once. Okay, so let's just quickly go through this. This was question number 6. Yeah, so right. So, which of the following were are the reasons why NDN may be more efficient than the IP in terms of network resource usage? So, one reason why it is more efficient is definitely the caching aspect. So, in NDN, data is cached at intermediate nodes. So because of this caching, like for one request, if the data is cached and kept further on, if n different people comes and requests the same thing, it's always responded directly from the router, because the first xyz goes all the way, and after that when xyz comes back, this gets cached here. So after that, any request for the content xyz gets responded immediately. So this actually saves a lot of resources. In addition to that, another thing that we saw was there are and if there is a publisher, and if two people are requesting, two subscribers are requesting for the same xyz, then only one request goes here. Only one goes here. Whereas in traditional scenario, both the requests will go through R1, R2 to publisher P1. Whereas in NDN, only one of the requests goes through R1, R2 and P1. But on getting the response, R1 makes sure to respond to both the requests. On getting the response, both of them will get the response. So that is taken. So here again, the bandwidth and resource utilization is good. So this um, caching is one thing. Another is interest data packets can be forwarded to multiple producers and consumers. So if we have multiple producers giving the similar content, it can be shared across. So that is also another aspect. Interest bar data packet can be forwarded to multiple. So here itself, if you see, one data packet is coming, right? But it is getting forwarded to two different consumers, right? So this happens because of this. There is actually better resource utilization in NDN. The third one is interest packets are always routed towards the content produces via the shortest path. It's not always by default it takes a shortest path, but sometimes it can take the longest path. I mean, not so shortest path also. So all always is not true there, so that is wrong. C is wrong. So A is correct, B is correct, C is wrong. D, NDA networking paradigm does not pose data privacy and availability risk. So that is there in NDN also. So data privacy and availability risks are there in NDN also. So D is wrong. So the answer is A comma B. So question 7, let's quickly wind it up. The next question. Which of the following statements is bar are correct about the naming in Indian? Naming in Indian. So Indian uses hierarchical naming. So we have seen that Indian uses hierarchical naming, and names are generated by applications. And users by application developers do not have the ability to define their own naming convention. So on naming convention cannot be defined by user bar applications. Okay. Then third one, flat addressing. So flat addressing is not normally used in Indian, but certain special case, I think it is allowed, but so in general, it is not. So the statement that Indian does not support flat addressing is wrong. It do allow it in certain scenario, certain cases. So it allows it in certain scenarios. So A and B is the answer here. Is the answer here. Now the next question, which is question 8. Um, the standard Indian architecture, how many data structures does each router typically maintain? This I think you can answer. Please type in. So we have seen, right, what are the tables in each of these. So when a subscriber is trying to send data, so we have FIB, then we have PIT, and we have CS, right? Each of the router have a forwarding information base, pending interest table, and a cache store. So how many tables are there, or how many data structures are there? One is FIB, second is PIT, third is cache store. So we have three. So B is the answer. And the next question. Just read through the question. Yeah, so the question is, which of the following statement is or are incorrect about the security in NDN? So, we know, we have seen, so content provider, first option is content producer, that is the publisher, cryptographically sign the data, that is option one. So we have already seen, right, for authentication and integrity, signatures are used. So signing is done by the publisher or the content producer. So that is true. The question here is which of the following are incorrect? Okay, so we need to find the incorrect statement. Statement 2 is so, okay, A and B. B is system cannot be attacked using information obtained from the identifier. So, since the signature based integrity and authentication is in place, even if somebody in the middle manipulates the content, it can be detected. Okay, so it cannot be attacked. Obtained from the identifier. Okay. So this is also true. C says that and NDN uses end-to-end encryption. So NDN only ensures authentication and integrity. End-to-end encryption is not there. D is encryption is mandatory for data to be transmitted on the network. So that is also not true. So the answer here is C and D, which they C and D are the incorrect statements here. Now let's see the last question. Okay. So question is, what is the role of NDN trust model? So we have seen that the NDN uses the signatures, and using the signatures, what do we ensure? We ensure the data authenticity and integrity. So the role of Indian trust model is to ensure data authenticity and integrity. Signatures doesn't ensure data availability, successful delivery, and resource management. So the answer here is C. Okay. So So yeah, with this I'm like done with the session. So maybe we have 10 more minutes. We can quickly just list down what all are the topics that have been discussed in the last 12 weeks. So the discussion started with high performance routers, right? High performance routers. And then we went into the routing table. Routing table, how are they organized? The data structure used, to implement the routing table in software, right? What was the data structure? That was thoroughly discussed in the, I think, first 2 weeks, right? Then we had binary trie, multi-level trie, multi-bit trie, then optimized trie. There were various optimized algorithms also, right? For reducing the length of the trie for storing the routing tables. Then packet classification algorithms were discussed. Then the quality of service, differentiated services were discussed, and then we moved to the concept of like emerging trends in networks, right? Try emerging network technologies. First session, I think, was on network ossification, why the current network in its form is very rigid. It's very reluctant to research and changes. Why we call the network as ossified. Then the concept of SDN. So in this, we understood what is a control plane, what is a data plane. Basically, SDN separates this control plane from the data plane. Then the concept of network virtualization, network function virtualization was discussed. Why do we need these network function virtualizations? Then we saw something called programmable data planes. Why SDN was not sufficient and why programmable data planes were required and needed. Then we went to the concept of monolithic versus microservice based application architecture. Serverless computing. And in this, we infrastructure as a service, PaaS as a service, then software as a service, all these concepts were covered. Then we got into this information centric networking. And then NDN, name data networks. Okay, overall, these were the various topics covered in the session. So, if you have any doubts, let me know. Otherwise, then we can wind up the session. Yeah, thank you. And So for all those who are giving the exam, all the very best. Yeah, so I'll wind up the session. Thank you for joining. Thank you. Bye.